Welcome back. Let us look at one more exercise before I leave the field open to you. Let us look at exercise D03. We have a thermally insulated cylinder closed at both ends. That means we have a rigid box and it is fitted with a leak-proof frictionless diathermic piston which divides the cylinder into two parts. It is leak proof, so whatever is in on one side of the piston cannot move to the other side and vice versa. It is a diathermic piston, so it will maintain the temperatures of the two subsystems on either side equal. The two parts are known as A and B. Initially the piston is clamped in the center, so the volume of the two parts are the same initially, 1 liter as well as 1 liter, V1A and V1B, and the states of one side and other side are given. Air is the fluid. Notice that the two sides have the same temperature, 300 Kelvin, but there is a pressure difference. Side A has a pressure of 0.3 megapascal, side B has a pressure of 0.1 megapascal. The piston is released. Now when the piston is released, it will try to move towards the low pressure side. So side A will increase its volume, side B will decrease its volume, and after some time, when equilibrium is again established, it's leak proof frictionless piston, so pressure would be the same on either side. It's a diathermic piston, so temperature would be the same on either side. And let's compute now the final pressure and the final temperature, and also the change in entropy. Which irreversible process has taken place? That's a question I am leaving open to you. I will just hint at the way this problem is going to be solved, and I will illustrate here that it will always be a good idea to list the unknowns, and then if the number of unknowns is say n, see to it that we are able to set up n equations to solve for these n unknowns. So I am going to illustrate this from that point of view. Let us sketch our system. I will show the piston by means of a thin partition, leak proof and frictionless. The whole system is rigid and insulated. So the full system is rigid and insulated. This is side A, this is side B, and initially there is a mass ME209x, pressure PA1, temperature TA1 and volume VA1 on this side, and initially mass MB1, pressure PB1, temperature TB1 and volume VB1 on the other side. And all these things are either known or from the equation of state we can determine. The volumes are given, the temperatures are given, the pressures are given. So if we assume air to be an ideal gas, we can determine PV equals RT, assume some molecular weight of air, say 29 kilogram per kilomole, and you are through. You can determine MA1 and MB1. Now let us list out the parameters in the final state. The final state, let the mass on the two sides be MA2 and MB2. Let the pressures be PA2 and PB2. Let the temperatures be TA2 and TB2, and let the volumes be VA2 and VB2. Notice that there are 8 unknowns. Now, which are the 8 equations that we need to obtain or we need to set up? Let us look at those equations. First, although A plus B together is a closed system, because the piston is leak proof, mass on side A remains unchanged, mass on side B remains unchanged. So, one equation would be MA2 is MA1. Similarly, MB2 is MB1. 2 equations. Then, well, we have assumed air to be an ideal gas. So, even the final state will satisfy PV equals MRT. So, we will have PA2 VA2 is MA2 R TA2, and in a similar fashion PB2 VB2 equals MB2 R TB2. 2 more equations. Then we are given that the piston is frictionless. Since it is frictionless, the pressures on either side would become equal when it finally reaches its stable position. So that means we have one equation which says PA2 is PP2. 5 equations. Then we are told that the piston is diathermic. So it will not tolerate any temperature differences on either side, and hence we will have TA2 equal to TB2. 6 equations. We need 2 more. And which are the 2 more? One is the full system is rigid. Consequently, the volumes of the individual subsystems may change. VA may undergo a change, VB may undergo a change, but the total volume remains unchanged. So we will have the final volume of the system equals initial volume of the system. So we will have VA2 plus VB2 equals VA1 plus VB1. So these are 7 equations. We need one more, and that will be the first law of thermodynamics. The first law of thermodynamics would be Q equals delta E plus W. Now, first we are given that the complete system to which we are applying this is an insulated system. That means it is an adiabatic system, and that is why this will be 0. Why? Because it is an insulated system. Now what about W? W will be expansion work plus other work. Because the system is rigid, expansion work is 0 because the system is rigid. What about the other work? Let us assume it to be 0, and that means we can get rid of this W term. That gives us delta E equals 0, and if we write this as delta U plus delta E other, then delta U can be related to temperature, but let us assume again that delta E other is 0, and then the first law reduces only to this part. The change in the thermal energy of the system does not change through the process, and delta U equals 0 means delta UA plus delta UB is 0, okay. And delta UA is related to its final temperature and initial temperature. Delta UB is related to its final temperature and initial temperature. Since the initial temperatures are the same, the final temperatures are also the same, we can write a simple expression for this. In fact, the general expression would be MA CV, I am using the same CV and making a minor assumption that let us assume CV to be constant, then delta UA will be TA2 minus TA1 plus MB CV TB2 minus TB1 is 0, okay. Now I have just used MA and MB here, actually they are, you could use MA1 or MB1, but since MA1 and MB1 are the same thing as MA2 and MB2, you could use either here 1 or you can put 2 there, does not matter. This is the 8th equation. So this is equation number 8 that gives us 8 equations and 8 unknowns. That gives us the complete final state, and once you get the complete final state, the change in entropy of the system will be determined as change in entropy of system part A plus change in entropy of the system part B. And since we know the initial and final state of part A, we can determine delta S A, and similarly we can determine delta S B. Compute delta S A, compute delta S B, sum them up, you will get delta S of the system. Since the system is an insulated system, and actually the way we have assumed that it is an isolated system, delta S system itself will become delta S universe, that would be the amount of entropy produced, that should be greater than 0. Check this out for yourself. Thank you.